This is Algebra 2, Lesson 12.1, Graphing Trigonometric Functions. So we are going to be looking at graphs of sine and cosine during this chapter, and then transforming those graphs. So I want to give you briefly what initially those graphs might look like. So the graph y equals sine of x. These are cyclical graphs, and so it's going to start at the origin, come up, but then go back down, and then come back up again, and then that's going to repeat in an up and down, up and down, up and down fashion. The graph of y equals cosine x has the same shape to it, but its starting point varies. The graph of cosine of x would start at the top and then come back down, but then it'll go back up again in that same fashion. And then the graph would go backwards the same way. You could also look at the graph of negative sine x, and it would do the same thing, but it would come down at first instead of going up at first. And the graph of negative cosine x would start down here and come up first. I want to just point out what those graphs, how to easily identify these graphs. So just looking at the black ones, not at the red ones, that I easily pick out the sine graph, because if you look in the middle, right in the middle, it has sort of an S shape to it. And on the cosine graph, if you look right in the middle, it has sort of a C shape. I mean, it's on its side, but there is a C shape there. So when you see the negative ones, it's still an S shape for the sine, but that S shape is kind of going down instead of going up. And on that cosine graph, it's still a C shape, but it's actually more of a U shape for the negative cosine, because it's like an upside down C. So it's like a U, or like a sideways C, so it's like a U. Either way, so we're going to try graphing one of these sine equations. We're going to specifically graph the equation y equals 5 sine x. We're using y equals 5 sine x to represent a rider's vertical distance in centimeters above a model Ferris wheel platform as it turns. So if we want to try to draw a visual representation of that, here's our Ferris wheel, and I'm saying that there's a boarding platform here. So people are getting on the Ferris wheel, and then it goes around and around and around, and we're talking about the height of the rider as the wheel turns. So notice it goes up above the platform. Once it reaches the peak, it comes back down. Once it reaches 0, it goes under the platform and then comes back up again. To get some values here, I'm going to use my calculator, and I am going to substitute the values along my x-axis, so my degrees, into the equation. So I'm going to start with 5 sine 0, and make sure I'm in degree mode, and that is 0. So 5 sine 0 is 0. Now I'm going to substitute 30 degrees into my equation. 5 sine 30 is 2.5. I'm going to sub 60, 5 sine 60, and as I keep substituting these values in, I'm seeing at 0 the start here, and then after 30-degree rotation we are 2.5 above the platform, and at 60-degree rotation we're 4.33 above the platform. So at a perfect 90-degree rotation, 5 sine 90, we're at 5 centimeters above the platform. That makes sense because we put this 5 in here. So it's saying we're 5 away from the platform sideways, or we're 5 away from the platform. Basically, the radius of the circle is 5. I'm going to keep going and substituting in 5 sine 120. And that gives me 4.33. Now if you notice, that's the same value we already had. If we keep going to 120 20 degrees right here, we're at the same height that we were 60 degrees over here. And it's going to kind of work out to be the same, so I'm not going to keep typing these in. You can check my work if you'd like to, but it's following a circle pattern, so it's going to just come back to where it started. And then actually when it goes down into the negatives, I will do this one, 5 sine 210. It's actually the same value we had before with the 2.5, we're just in the negative, so it reflected underneath that x-axis. So all of these values that we already had are the same, they're just the negative versions because we went under the axis. That should have been a 5. And then 360 degrees is one full circle, so that brings us back to our starting point. So now I'm going to graph these values and we'll see exactly how it looks. So at 0 degrees, I am at 0 centimeters. 30 degrees, I'm at 2.5 centimeters. 60 degrees, 4.3. 90 degrees at 5. And then once I have those set up, it's not too bad to keep going the opposite direction. And then at here, we're at negative 2.5, negative 4.3, and 5. Negative 4.3 again would be here, 2.5, and then back to 0. So I used my calculator to generate some values, plotted those points, and now I'm going to do my best curve connecting each of those points. And that is the first cycle graph of y equals 5 sine x. So we can use this graph or this table or the equation, graph table or equation, to answer some of these questions below. So question I, what is the rider's distance from the platform after the wheel turns 870 degrees? My table stopped at 360, my graph stopped at 360, so I'm going to use the equation. That would be 5 sine, and we're going to substitute 870 degrees into the equation. 5 sine 870 means after 870 degrees of turning, the rider will be 2.5 centimeters from the platform. Question 2, what is the rider's distance from the platform after the wheel turns 37 degrees? I could answer this with the graph or the equation. I'm going to scroll up just to use the graph. So I know where 30 degrees is. 30 is right here. 45 is right here, so 37 would be pretty much right in the middle. So I'm going to say that comes out to be almost exactly 3 centimeters. I'm going to check the work with the equation just to see how close of a curve my graph drawing skills. So 5 sine 37, I'm hoping to see something pretty close to 3. And I got basically 3 exactly, so that's good. Question 3, when is the rider 3.5 centimeters above the platform? I'm going to use the graph to do that one. And 3.5 would be right about here. So if we follow that back, we get an answer at right about 45 degrees. But that's not the only answer, because if I keep this going, there is another answer here, and honestly, because the sine graph is going to keep going, there'd be another answer way over here around 400, and then another answer after that, and after that, and after that. So you can use the calculator to get the first answer, but just like when you square root an answer, it only gives you the positive version. When you use a sine inverse, it only gives you the first answer, not every answer that comes after that. But we're going to try to solve this using some of our algebra skills. 5 sine x is 3.5. We would divide both sides by 5. And then last chapter, hopefully you remember, if we're trying to find the x, We use the sine inverse to undo the sine. So I'm going to do sine inverse of that fraction. Sine inverse 3.5 over 5. 44 degrees, and I was right about 45 with my estimate on my graph. But then remember, there was a second answer at, let's call that 135 degrees. 136 probably, since we were off by 1. And then there would be a third answer and a fourth answer and so on. So the equation only gave us the first answer when we solved on the calculator, but we can use the graph to see that there's actually going to be many, many answers that hit 3.5 centimeters. And the last one is, when is the rider 8 centimeters above the platform? Now if we look at the graph, we can see that it tops out at 5 centimeters. And that's because that's how tall the Ferris wheel is. So you're never actually going to be 8.5 centimeters above the platform because it's only 5 centimeters tall. So this one would be no solution. And I am not going to write out the work, but I'll type it out. If we use the calculator and use the same idea, where we would have the sine inverse of 8 over 5, that's not going to work out. We're trying to put in a hypotenuse larger than a long side, if you think back to our chapter 11 work, so it's never going to be 8. It's not going to happen. So that was a long video, but that's it for my notes. Good luck on the exercises, and let me know if you have any questions.